Swayam Prabha. Digital India. Educated India.
Let's continue with the main purpose of an operating system, that is program execution. And the idea of this session is to look at how do we go from programs to processes and threads. Although I've put up the threads title here, what I ended up is having another set of slides for threads, just a few slides just for threads. So we will go through this set of from programs to process, and then graduate up to threads in the next session. I won't say next session really, just after this bunch of slides. Honestly speaking, I mean, setting up this session was challenging in many ways, and I have chosen to sort of do a somewhat ambitious thing. So I'm going to start from actually writing programs and then going all the way up to processes. So this is going to revisit a number of things that you already know, and we'll also be going into a little bit into actual writing programs. But nevertheless, I hope giving a full view helps you to understand some of the processes, some of the things that we do. All right. So what we already know are things like CPU and computer organization operation and stuff like that. What we have is a source program, and I have some sample.c program that is there. We know some amount of program processing via compiler, say GCC or whatever it is, and an operating system, Linux based. Windows is fine too, but command line is very, very useful. Once you have a control over your command line operations, then the rest of the development effort is much easier. So let's revisit these things that we already know from a perspective of execution. So let's begin with hardware, CPU and computer organization operation. Actually, just CPU operation is going to suffice for us. So I'm going to view it like this. There is a CPU with some kind of an internal structure, an instruction pointer IP and some scratchpad. There is fetch unit, decode unit, execute ALU, some registers and so on and so forth. There's a primary memory labeled PM with some contents at some places. And the way sort of the CPU operates is that at various clock ticks, at the first clock ticks, the instruction pointer fetches the instruction, and that's what the fetch cycle does. Then it goes into a decode cycle where that instruction 0x5A is decoded. Ours is a fictitious CPU, so this decoding of 5A into firing an adder circuit is just a illustration. So presumably in this CPU, the code 5A represents run the adder circuitry that is there. So how do we do that? So the first part of the execute cycle will load up the operands in the registers. Next, the operands will be given to the arithmetic and logic unit, which has the adder part there, which will perform the addition and put up the result in the register. And then the register will, contents of the register will be put back to memory. The key point here is that this hardware, when it works in lockstep synchronization and is requires us to be very precise. Exact addresses of the instructions, exact addresses of the data, from where the data is to be picked up, addresses where the data is to be put back. All of these needs to be precise and clear. Only then the operation, the way the CPU runs, the way it executes, that will make, in quotes, sense. By the way, when we say that it makes sense for us as human beings. As far as the machine is concerned, there is no notion of sense. The only thing it does, it goes on changing the state. At every clock tick, depending on whatever is there in the primary memory, the state of the system keeps on changing as it progresses. It's a physical system, so that's all it does, state changes. Anyway, so that's the kind of idea that we have about the machine, the CPU and the entire operation of the machine. As far as the source program is concerned, here is one. I mean, this is just a C program. You don't have to know C to understand this part. You just have to know that there is some program, and the rough structure of the program is something that is really useful. I wrote this C program, and there the point is that it does a call to another function called modify. It modifies its parameters in some whatever way it is. But right now in this particular file, there is no modify that you see. All right. That modify is there in another file, and here is the function modify in another file, modify.c. So how do we do that? I mean, now we need to process these programs. How do we do that? Well, here it is. In one single terminal window, I'm trying to show it, but let me step through. I'm going to use a GCC compiler, which is going to compile this sample.c into an object file called sample.o, and it's going to create an intermediate sample.lst file. That's I did that so that I can illustrate some points later. In the next command, I'm going to do the same for modify.c. I'm going to get a file modify.o. If I list out the files, you will see that they have been created. Voila, great. Now I'm going to create the executable file where the object file sample.o and modify.o are going to be combined together into an exe file. Okay. And again, I'll list it out, and there you see, yes, it has been created. And when I run sample.exe, it runs with whatever is the output that is there. Note that the phrase that I've used is executable has been run. Okay. All right. And finally, the OS on which all of these things is, of course, our standard GNU/Linux in the case that I have in mind right now, but it could be any other operating system also. The details may differ, but the ideas are the same. Let's now look at the files that we have asked GCC to create a little bit deeper. This is still not program execution. It is just from our C or whatever is the HLL high level language that we use, from C to the final process. We are just starting that path. What we have done is we just have a sequence. From source, we went to assembly. From there, we went to object files. From there, we went to executables. And from there, we went to a process. What is source? I mean, it's a program at a very high level. What does a program do? It just states what is to be done in order to achieve a result. It uses data types at our human level. The control flow is logical, so you have branch statements, you have loops and function calls and so on and so forth. But you do not have things like memory addresses. Remember, our CPU required memory addresses, very precise memory addresses. A high-level language has nothing like that. It just has logical fellows called identifiers. The target hardware is again very low level. So of course, I mean, we need to have a chain of programs that transforms this, realizes the sequence so that your C programs can be run as processes. Let's look at the kind of thinking model we have for each of these phases. So when you think of a C program, that is a high level source program, your program is at a logical level. Operations are at human level, data types are at human level. Whatever are the entities in the programs, they are labeled, they are given names, symbols, identifiers are used, and there is no concept of an address. Here by address I mean memory address. All right. When we come down to assembly programs, our model is slightly different than high level ones. We have, instead of logical human level operations, we have machine level operations in terms of mnemonics. Okay. And our data types are not human level, they are very nearer to the machine types. Locations or addresses are there is a idea of an address, but nevertheless those addresses are logical labels. They are still logical labels usually. Okay. Of course, I mean, nothing prevents you from actually giving exact addresses, but typically there are logical labels. When you come down to object files, you do not have mnemonics. You instead have explicit binary operations. You have explicit binary when data types are in explicit binary, and the locations addresses are in binary. So in that sense, an object file is almost exactly is in the form that is exactly required for the final CPU, but there are things that are missing. So it's possible that some symbols of the assembly of the C and assembly may not have addresses. For example, when sample.c is going to be compiled and assembled, both C program and assembly program will have a label called as modify, but that modify will not have an address because there is no physical code that will carry the label modify. So it is possible that your that your program that you had in an object file, it may have symbols whose addresses cannot be computed. Therefore, an object file will just have a set of table. Will have a table. It will have a set of symbols that have an address, and a set of symbols that don't have an address. In that sense, an object files are incomplete. The linking process combines object files into an executable files and essentially completes this process. You after linking, you ideally should not have a symbol whose address is unknown. Okay, ideally. Oops, I made a mistake there. So the thinking model for executable files is explicit binary for operations and machine data types. Locations addresses are in binary. Symbols whose address cannot be computed are tabulated. That's not true. I mean, ideally you do not have that. But if there are any, they are addressed to what is called as a. We will look at that a little later. What to do with symbols whose addresses are not computed in an exe file. But in a process, you are going to use the operating system memory management algorithms to allocate memory. Many processes can be generated from one program, and addresses in program code need to be updated when memory is allocated. This part is something that we are going to examine in a little detail now. Here are the details. I mean, when you look at a compiler, you are only going from source to an assembly. Your data types are changed from integer character strings at high level to one or more integers strings in assembly. Control flow from high level loops and function calls to low level targets specific machines, sequencing and branch, and addresses as labels. Operators at high level become machine instructions in ASM. In an assembler, your data types, that is integer strings, become one or more bytes. The control flow, machine sequence and branch becomes explicit instruction codes and numeric addresses, and machine instruction become instruction opcodes. Let's look at examples and see how assemblers and linkers work. That was the purpose of creating those list files. So here is the a view of sample.c, or when it gets so when the sample.c is assembled to an object file, how it is done. So you will see that the assembly part has various sections called as .text, which is instructions. .data is the data section. So whatever is the data in your C program, that gets mapped here. BSS is uninitialized data, and there are a number of other directives, global, type, align, and so on and so forth. This column is the address calculation. This is the address that is calculated in virtual memory. When we looked at paging, we looked at that blue colored M dash. It is in M dash these calculations are done. What the addresses that you see are the addresses in M dash. All right. The starting address is start from 0 and the range of the address is that section. So the data section, however long, is the range of the data section. The text section, however long, is the range of the text section, and so on and so forth. The second one is data. So it's the read-only data. You can see that just a couple of lines above you see dot section dot ro data. Ro data is read-only data. And the data element string a equals %d, comma b equals whatever, that entire string is now represented in binary as 61203d, z20256442c2, etc. But that's all that the data is there. After that, the text, that is the code, starts. It says global main, that is the label main is global. Everybody knows about label main. This is the starting address of the text section. The text section starts up with the instruction end br64 followed by push q %rbp and so on and so forth. The instruction is assembled. The instruction here in mnemonics is assembled into the in whatever is that assembly, whatever is the binary is represented in the second column. 55 is the assembly for push q, for instance. Actually, it's not 55, it's 55. 55 is decimal, whereas 55 is hexadecimal. This binary is the one that you will find in your object code and executable code. Of course, this is the one that's going to be executed by the CPU. Notice that there is a label call to modify in this assembly code. There is also a call to printf. But the point is, where is this label in this file? In this file, that label does not exist. Neither does printf exist. All right. So this object file or this attempt to create the binary is going to be inherently incomplete. Because it is incomplete, we will call this kind of a binary as an object file. If you look at the other file modify.c, there you will see the label modify. And not only the label modify, but the corresponding code is also there. All right. The linker is going to take all the object files and resolve it. So it will look at sample.object file, see that, okay, this object file sample.o needs the label modify. Then it looks at modify.o and it sees modify.o has the label modify. Okay, when I put them side by side one after the other, I can use the modify label in modify.o and fix up the addresses in sample.o. That is what the linker does. Here is the result of linker. If you go from top to bottom, you will see that the linker allocates data for common symbols like A and B that we were there in sample.o. There are some sections that are discarded. The GNU stack, node.gnu stack, .node, they are discarded. Then it starts looking at the memory configuration. The default memory configuration is 0 to FFFF, whatever it is. All right. Then it starts loading a number of object files. It not only loads sample.o and modify.o, but also some others that we had actually not given. But these files, object files, contain code for actually starting main. We will look at that a little later. The linker included the printf from the standard C library because that was needed by sample.o. Linker created common symbols, and here is the text section. Here are some files, and here is the text section that the linker created. The linker started with address 000. At address 1060, it had some 1F5. Each of the files were laid out one after the other. In particular, the main in sample.o is at address 1149, and modify from file modify.o is at address 11b5. Notice that the final executable which combined sample.o and main.o now has all the symbols with their corresponding addresses, and hence can be given to the hardware for execution. All right. This is the point where we come to the loader. This is the point where an executable can be converted to an OS. What does this executable to process do? The loader is going to use the contents of exe, the executable file, to allocate primary memory. Then load the contents of the executable file into the allocated primary memory. Set up initial values of data. Specify the first instruction to execute, and then add to the scheduler queue. Over here, I'm assuming that you have an idea what is a scheduler queue, what is a scheduler and scheduler queue, but we will come back to it in a short while. Notice that the loader is actually just reading the exe file, and depending on what is there, it is creating some things in the primary memory. Let's look at that process a little pictorially. I'm showing a primary memory of a computer system. There is a CPU which is driven by a clock. Some initial part is there some initial part of the memory is used by the operating system. Some part is by data structures of the operating system, like the scheduler queue. I've labeled it as SQ. And there is some region of memory that is used by programs. Now the word programs is in double quotes. We are given an executable file, okay, possibly sample.exe. The set of operations that we need to do are something like this. First, the operating system will load the exe file for reading. What does it have to read? It has to read what are the parts of the executable file. So it will read them once it is loaded in memory. Once it is loaded in primary memory. Okay. It will see that, okay, this exe file has a text section and data section. The text section is so much big and the data section is so much big. Depending on the sizes of the text section, it will allocate that much amount of primary memory for code and that much amount of primary memory for data. Okay. Now it does not need the executable file in the memory, so it gets rid of that, and now you have just code and data of the executable file. Any memory regions that are needed, initializations that are needed are done. You record this layout into a data structure called as a process control block. Okay. The first instruction in the executable is noted in the process control block. And this data structure is given to the scheduler queue. Let's imagine that the scheduler has a queue, which means that the process control block, which defines this process, is in a queue. Whenever that its turn in the queue comes to execute, the scheduler will extract the first location to a first instruction, the address of the first instruction that was recorded, and jump to that. Note that the scheduler is just another piece of code. all it does is it jumps to the first instruction of the executable. That is how you start running the process for that executable file. We actually saw these kinds of things yesterday when Neha did some amount of things for Spark, but the ideas are the same. I am just connecting those parts to what is done in operating systems. So the CPU executes program and the scheduler schedules it, and when the turn of the program comes, okay, and then the machine begins to change its states according to the program. Note my words. The machine begins to change its states according to the program. This is when we have a process. Okay. When there is a set of states that actually change in the system as a result of our program, that set sequence of changes is what is a process. All right. A program is just a specification of what changes we need to get the end result. Fine. Well, that's that. You can do better also. I mean, you can enhance the sequence. So instead of just one very linear sequence, we can have multiple object files. We can have multiple source files. In fact, they can be in different languages, like you have C and assembly over here. But at the end of the day, the way the reductions go is the same way. All right. So this journey took us from program to processes, and along the way we saw how loaders or operating systems would work. Loaders are typically part of operating systems. So let's go back to the idea of a process. The textbook view was instance of a program in execution, but now we know what is meant by an instance. The instance was when the executable file was used to create an instance of the process. Given the operation of the loader, it's fairly obvious that the same executable can be used to create multiple processes. Multiple instances of the process of the program can be created, and after scheduling, they become processes. The word process, think of it in our lives. Let's look at it in a very common way. Well, if someone tells you to do something and you perform those actions, okay, so please give me a glass of water. When I request you that you do some things and get me the glass of water, those sequence of actions that ultimately result in me getting a glass of water is a process. All right. Whereas my statement, please get me a glass of water, is just a kind of a specification. It's just a program. These are the real life scenarios. I mean, if you look at almost everything that we do, the set of things that we do and cause changes in the environment around us is the process. All right. The difference with computing is that not all the processes in real life are algorithmic. Okay. In other words, not all can be mechanized into a machine. But the traditional way our idea of a process is explicated is by using a cooking a recipe example. A recipe is just a bunch of steps to be taken in order to create a dish. All right, and the cook actually looks at the recipe and performs those actions. So if you want to possibly do some, how do I say, aloo ki sabji, potato, vegetables and stuff like that, then the recipe will say take X number of potatoes, boil them, cut them, or whatever it is. And whatever is written in the recipe, the cook will perform those actions. So he or she will take those potatoes, put them in the boil them and peel them and cut them and whatnot. Note that as a result of the cook carrying out the process stated by the recipe, you get a dish. There is something concrete that results. All right. So the recipe is just a description. The process is actually carrying out that description and changing physical state. That is what really a process is. All right. At this point, I should also mention that in practice, when most people talk of processes, they also say that the loaded program, the program that has been loaded from the executable into the primary memory, that is also at times called as a process. All right. So people do use the word process interchangeably, but as far as understanding is concerned, it is useful to think of process exactly the way I've talked about, that there are physical changes that occur and the end result of those physical changes is the end result that we want. All right. So specifically a process in an OS and in computing. So a program is just a set of commands with data to operate upon. And the machine and associated devices are the ones who perform the actions. That is a process. And a process causes a sequence of changes in the system state. Register contents change, IO device change. So when you say print a file, there is some set of processes that occur in the physical system and you get your printout. Okay. And as programmers, what we are interested in is we imagine the process and write the specification as a program. Okay. So here's a simple model now to understand operating system. This is a much simplified model, and to my mind, it's something that is useful to understand how the execution idea is created in operating systems. In the subsequent sessions today, Abhishek will also do inter-process communication, but the later reviews will show how networking has contributed to expanding the idea of execution and so on and so forth. So that's there for the next days to follow. All right. So conceptually, I'm going to treat a program that we write as a C function that an OS calls. So to my mind, an OS is a C program which is going to call some function, let's say function to call. But this function that is going to be called by the OS is written after the OS itself starts running. Take a little moment to understand this. An OS is like a C program which is supposed to call a function. The only situation is that this C program that is going to call a function itself is actually running. Fine. And while it is running at point A, the function that is supposed to be called, you start writing that function after this OS starts running. Right. But nevertheless, the OS as a C program has to call a function. Okay. But because the function is written after the OS starts running, the OS does not know what function it will call, but it knows that it has to call some function, and there could be possibly more than one. So here is a challenge. How do you write a C program that is supposed to call a function that it does not know about? And what's worse, that function that it is supposed to call will be written after the program starts running. Can you do something like that? All right. As a language, if I think of C as a language, it is just a bunch of functions calling each other. And there is only one privileged function called as main. Why is it privileged? Because that's a point where the C program starts from. But then you can imagine it like this, that the OS is a C program and it says that, look, I don't know what function to call. All I'm going to say is that I am going to always call a function called as main with whatever is the argument, int argc char pointer argv. Okay. So an OS that is going to treat its programs as a C function call is going to mandate that, look, I'm going to only call functions with so and so type. So at least if and it's also going to say that I'm always going to name the functions as main. So the OS does standardizes that function call. I'm going to call a function called as main. All right. That main will have two arguments, integer and a pointer to an array, character array. That's it. Then what happens inside that is that function's problem. You also want to write that OS as a C program model. You also want to write it so that it can call a number of such programs. It does not have to call just one C function. It can call your C function, my C function, or in other words, your program, my program, any number of programs it can call. All right. Why am I thinking of it like that? Because it allows me to think of operating systems and our programming completely as just a C program, a sequence of C functions. That's it. Fine. This helps me to think about the next problem, threads. Let's see how processes are run. So more than one process, more than one functions can be scheduled by an OS, and that is, they are not a problem if they don't interact. What do I mean by interact? When processes exchange information, I say that they are interacting processes. Okay. Interacting processes are challenging because you need to worry about synchronization of data access. You need to discipline the resource usage so that deadlocks are prevented and so on and so forth. Interacting programs are quite challenging, but nevertheless, they are extremely valuable also. This interacting processes or inter-process communication is something that Abhishek will continue with. But in the meanwhile, let me look at how processes run. So here is a simple factorial program. There is a main which just takes up one argument, some number from the command line. The number is f, and it computes its factorial. The factorial is a function which is written as using what is called as a C ternary operator. For those of you who are not familiar with that, you return 1 if x is 0 or x into factorial x minus 1 if x is not 0. All right. So this is the factorial program in C. So here is the process that has been generated from this factorial program. How do I generate the process? We had seen that in previously, the entire path from source program to a process. Here I'm saying that that entire path has been traversed, and in the main memory that you see vertically, you have the process. Within the main memory, there are parts of the memory that are allocated to the code area of the process, that is instructions of the factorial process. There is some area that is allocated to the data of the factorial process, and there is some part allocated to the stack. What do I mean by stack? Here the stack is the stack of activation records, the activations of various functions. So the main activation is at the bottom of the stack. Just on the top of that is a factorial of 6. I'm assuming that the program has been called to process to compute a factorial of 6. So the factorial of 6, computing the factorial of 6 calls factorial of 5. So there is another call to itself. It's a recursive call, which means that one more activation of the factorial function is made. I made a mistake. It's not capital F. Please read it as small f. But so as many activations of factorial occur as are required until you reach factorial 1 and factorial 0. The moment you reach factorial 0, you return 1 and the entire change starts coming down. Note that the stack is going to grow as the as the process executes. All right. This is the runtime behavior. That's something that we normally understand as runtime behavior. But this exactly is the difference between the program as a static entity and process as dynamic. It is actually causing state change. All right. And then once you compute factorial 0, the entire stack now unwinds itself and comes down to a point where the actual value of factorial 6 is computed, returned back to main, and then main picks up the factorial, the result, and then does whatever, etc., etc. Okay. But then one does not have to generate just one process from the program. One can generate another process from the same program. And here is the same picture, but for another process. All right. And the same primary memory, although I've shown different primary memories, that's more for convenience, but otherwise the primary memory is same, except that the regions of the primary memory where they exist are different. Here you will notice there is an interesting part that is happening over here. There is a part of the state, that is the entire context, that is different between the two. And that difference is only as far as the stack is concerned. Is this okay? Does this make, are you agreeable with this? In this example, the only difference is with respect to this part. So there is an obvious optimization. Let the two processes share the code and data sections, but keep the stack separate. The stack for one process is different from the stack for another process, and otherwise they share code and data, and we're pretty good. This obviously makes it easier to use the resources of the computing system, yet the processing is same. The processing is okay. There are, of course, you can think of many challenges here. Say, I'm assuming that the data area of both the processes are untouched. There is no change ever in the data area. But if at any point the data area changes, then that's not, this model only extends that apart from the stack, some part of the data area also changes. All right. But the other interesting part is, once you realize that only a small part of the context is changing, then can we use this as a technique of thinking about writing programs? These, by the way, are called as threads. Threads are things that, processes that differ by their stack, and that is their local state. And because the differences are very small, the context switching between threads is faster because only stack needs to change. And that's why threads are also known as lightweight processes. But this is as far as only execution of the processes is concerned. The turning the coin back, can we think of designing programs for threaded execution? That is, you write programs by explicitly understanding that only a small part of the context changes and just switch between them. If we do that, then we will have processes with different threads of execution. Okay. So consider a program that wants to multiply two matrices. The fact that matrices need to be conformable for multiplication, etc., all those kinds of things are taken care of. So suppose there is a function A that produces the row column product, that is the answer of the multiplying row and column for a given row and column. Then this function can be threaded. For different values of row and column, it operates on different data, and the only thing that will change is the local state of that function A. And if you now have multiple copies of function A running, but with different row and columns, you will have a threaded version of your matrix multiplier program. That is what I think so. But I'm not very sure about it. So I would want you to think about it and let me know, is this a candidate for threaded execution? Okay. What I've tried to do over here is to give you a very concrete idea of what exactly is a thread. I have shown you one way of creating those, one way people realize threads. There are different ways you can think of, implementing this idea of threads. Essentially, they will be, in a sense, same. You're going to deal with a small part of a local state that keeps on changing. The only thing will be how do you define the local state and how do you ensure that it remains local. Okay. It is because only a small part of the context needs to be changed. That is why switching threads is faster, and that's why they are known as lightweight processes. But otherwise, as far as multi-programming is concerned, well, I don't see much difference actually between threads and processes, but that's my view, because the real issue is a process, and a part of the process is because the context is small, you can have multiple parts of the process running simultaneously. True simultaneous when each thread goes on a multi-core system. In a multi-core system, you can have true simultaneity, but otherwise pseudo-simultaneous, pseudo-parallelism is what actually occurs. So with that, let me sort of stop over here and take up any questions. The idea has been to bring out the notion of process as a central entity in the business of operating systems, or even otherwise, that we actually want to execute processes, and in order to do that, we create all this software, operating systems and system software and stuff like that. One moment. Yeah. Questions time. Let me stop sharing. All right. So what we did was to look at the way operating systems come to, what we have learned in operating systems comes together in order to run programs. That is, execute processes. The precise thing to say is that processes are the ones that execute, not programs. But it's once we understand the idea, it's okay to be a little loose while talking and say we execute programs or we run programs. If you wish to be more formal, you might say that execution is the same thing as interpretation, because ultimately a CPU is a machine language interpreter. You always need an interpreter for running programs. Whether it is a CPU or something else does not matter. So thank you so much. Let me stop over here and if take up any questions.
Hello, sir.
Yes.
Sir, how does context switching happens in single-threaded applications? For example, Node.js, JavaScript by default doesn't supports multi-threading, but still Node.js provides async await keywords, and as well as it is used for building the server scripts. So it takes too much of load, but it still run on single thread. So how does it manage that?
Okay, unfortunately, I don't know Node.js and those technologies well enough, but from what you describe, let me sort of at least try to take a guess about it. Uh, or rather, more than a guess, I'm going to propose an hypothesis that you can also check whether that's how things are. So, you said that it has asynchronous calls, async await, and so on and so forth. Um, The single threaded part only means that it's a single process, really. Okay. I mean, there is nothing like a single thread just means that it is just a different word for a process. Okay. That
Yes.
means it's a process that is executing, and a call like asynchronous wait is a system call. All that is happening is that your node.js is calling the operating system and saying, please operating system, uh, whatever I'm processing, please make that processing wait until further
Yes.
notice. All right. So it's the operating system that is performing a wait. Uh,
Or maybe so, like we do with functions or routines, like we switch the context. For suppose for factorial function, we are switching, we are branching, and we are switching the context out there. So maybe something like that might be happening with the asynchronous calls out there, like hey operating system, this is an asynchronous operation. So this operation will so perform the operation what it is doing, like, and when it finished, then just switch context back to here only.
Yes, that is quite a good model. The only thing I would want to mention here is that, see, the word context here is a little, I mean, one needs to understand the idea of a context intuitively. A context is something that makes a process out of a program. A context is just the information that is, that the process is dealing with at that point of time.
Yes.
Uh, I mean, I can give you the Marathi word for it, Sandarbho.
Yes.
Okay. So, in fact, when we human beings talk, there is also an implicit context. So, to give an example of one of my students, um, suppose I say Sharif is decent. Okay, Sharif is decent.
In what
Then,
context?
yeah, it depends on the context. As
Yes,
it
yes,
happened,
Sandra
I had a
depend.
student named Sharif, and I was talking to him about him, that he was a decent student. Okay, but I
Mhm.
could also be talking about language, that there is a word called Sharif and it means decent. Now,
Yes, sir.
what exactly is the intention is dependent on the context, and when you and me we are talking together, we through our talking we have built up that context, and you understand exactly the way in which I am talking about Sharif is decent. So, in your mind, there is a certain context within which you're understanding the sentence Sharif is decent. The this idea of a context is exactly the thing that is there in computing also, except that the context is built up out of values of variables.
Yes.
All right, and the values of variables are the ones that make that process unique.
Yes.
The context is what makes it unique, and when you switch context, the operating system is doing is taking that whole bunch of data, storing it somewhere. Actually, in the process control block, it is storing it somewhere and using another context for another process.
Mhm.
Okay.
Maybe some so basically, sir, just taking the example of Node.js only. So by default it provides two methods by which you can do the asynchronous operation. For example, let's take reading one file, so it is one asynchronous operation, right? So
Mhm.
it provides one then callback, so that then callback you can mention what steps to take in after that function or after that asynchronous operation completes. So if I say that read file and then do this, so that part comes in then callback, and along with that then callback, to simplify the code structure, they provide async and await keywords, which are doing basically the same, I think, which are used for the same purpose. But how they do it, so I'm not sure about it. But maybe something like then callback, that the programming language is manipulating for us by itself, maybe, so that the code may
Ah.
look synchronous.
Oh no, 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 no. This is much more easier. I mean, you're thinking a little more complicated. This is actually very simple. See, when you are doing an operation like file operation, file IO,
Yes.
as far as processing is concerned, doing data transfer is an independent activity as when you compare it with doing processing. That is CPU executing instruction. That is one activity of the process,
Yes.
and the data transfer is another activity, right?
Yes, yes.
Okay. Now, there is no reason why you should have the CPU activity just waiting,
Waiting
doing
for
an
the.
infinite loop for the data transfer to occur.
Yes, yes, right.
They are, because they are independent, we say that they are asynchronous, which means that what we are trying to tell is, look, I don't have any CPU activity while this data transfer is taking place. All right.
Yes, yes, sir.
If that is the instruction you give an OS, then what the OS does is it puts you out of the scheduler queue, that is the run queue. It puts you in what is called as a sleep queue. A sleep queue is simply not scheduled. Bus. All right.
Okay.
Okay.
Mm-hmm. Yes, sir. Got it.
So the OS keeps on running processes that have CPU activity, and your processes put out of that CPU activity into a sleep queue as a result of async call.
Ah, yes.
Fine. And you
Yes.
say, you as a programmer, you write a callback that whenever the data transfer activity finishes, then the OS is told that, look, you are supposed to execute this function, whatever is the function callback that you wrote.
Yes, right.
Fine. So now it becomes an event driven system. The moment the data transfer finishes, the finish event
Should
triggers
be
the
triggered.
call to your callback.
Yes, yes, right.
And what does that, the first thing it does is, before the callback is made, before the callback function is called, the first thing it does, it removes the your program, sorry, your process from the sleep queue to a run queue, so that it
Yeah.
becomes schedulable.